One of the things that can help when trying to determine the amount of torque generated by a particular force is to very clearly define which set of axes you'd like to use. And there's really two main types. You have the traditional X and Y axes, but you can also rotate them and consider what we would call like the parallel and the perpendicular axes. And I'll show you what both of those mean. So if we take a look at this example here, we have an axis of rotation. We have some kind of rod that has a distance of d. There's a force acting at one end of the rod, and there's some angle formed between that force and that rod. So if we take a look, we could use our traditional X and Y axes, and all I've done is I've taken my axis of rotation, I've taken my location of my force, and I've quite simply just drawn in the X on the Y axis and the X on the Y axis. So I'm concerned just with the X's and the Y's here. If we take a look, we want the force and we want this perpendicular distance. So by using the X and Y coordinates, you can see here that we have a triangle. Using this angle, this perpendicular distance would be the distance, the hypotenuse, times the sine of theta. So if I rearrange my torque over here, it's the force times the perpendicular distance, which in this case would just be the force times distance times sine of theta, this angle. So if I take a look, if I use my X and my Y coordinates and I use the triangle that's set up, my perpendicular force and distance component will come out to be force times distance times the sine of theta. That's if I use my traditional X and Y axes. I could also rotate them and consider things that are kind of parallel and perpendicular. So what I've done is I've rotated them. So I now have basically for this axis, I have everything that's perpendicular and I have everything that's parallel. And I've drawn the same over here, everything that's perpendicular and everything that's parallel. In this example, my force was on one of my axes, so I didn't have to do anything. I did not have to find any components, but my distance was at some angle. It was not on the X or the Y, so I had to find a component. I'll have to do the opposite in this situation. Now, my distance is on what I would call my parallel axis, and my force is in between the two. So I can find either the parallel component of my force or the perpendicular. The parallel component to this distance or the perpendicular. Now, based on this angle, the parallel component would be found using cosine, and the perpendicular component would be found using sine. So if you take a look, this distance times the perpendicular component of force is what will give me my torque, and if I rearrange my torque equation, it's going to be this distance times the y component of this force will be distance times force sine of theta. So if you take a look in the first example, I found my component of distance instead of finding my force component based on the axes that I had chosen. And my torque came out to be force times distance times sine of theta. When I used the second type of axes, I had to break my force into components and not my distance, and I wound up with torque equals distance times force times sine of theta. You may notice that in both of those cases, I had distance, force, and sine of theta, distance, force, sine of theta, and it doesn't matter what you're multiplying, so you essentially, the order you multiply in, so you get the same exact equation, whether it's distance and force times sine of theta, or force and distance times sine of theta, you will always wind up with the same equation. So the important thing, the takeaway here, is that torque will always equal force times distance times the sine of theta, provided that that angle you're considering is the angle between the force and the distance. So in this case, here is my distance vector or my displacement vector. Here's my force vector. If the angle I'm referring to is the angle between those two, then this equation will always hold true. So force times distance times sine of theta, but you have to make sure that that angle is the angle between the force and the distance that you are considering for that particular torque. So to look at an example using this, we just have a bar that's 4 meters long. We have an axis of rotation down here, and I have a 30 Newton force acting at 52 degrees. So using the equation we've just discussed, it is still force times perpendicular displacement or distance, but we've kind of defined it now in terms of that specific angle between force and distance. So if this is my equation, and we know that that angle must be the angle between, well, here is my distance, here is my force. If it's 52 degrees, well, if I were to extend this, the force does act at a 52-degree angle from the plane of my distance vector, or my displacement vector. So if I list my known quantities, force equals 30 newtons, my distance is 4, and the angle between the two is 52 degrees. So if I plug that in, well, the torque is equal to 30 times 4 times the sine of 52, and that will come out to be 94.56 Newton meters. Now that's if I consider this angle. One of the questions I get a lot, well, what if I consider this angle over here? Because that does also appear to be the angle between both the distance and the force. And I'll certainly take a look at that right now. So what I've done here is I've redrawn this diagram, but only this section over here. Everything else still applies. I just didn't see the need to redraw everything. So here we have just the end. If this is 52, that would have to make this 128. So I've listed my same variables. The force is the same, the distance is the same, but instead of considering this acute angle, that's 52 degrees, I'm considering the obtuse angle, which is 128 degrees. And both of these are technically angles between the force and the distance. And if I plug in the same force, the same distance, and that new angle, you'll find your torque comes out to be the same exact value. And that's because as long as I use the angle between the force and the distance, I will be able to accurately calculate the torque. Just please don't forget that that angle must be between the force and the distance. As soon as you use another angle, you're going to run into an issue. Such an issue would be something like this. If you were given a problem which is very similar, 10-meter pole, 20 Newton force, the pole forms a 50-degree angle with the horizontal and an axis of rotation down here. The biggest, most common mistake I see is torque equals force times distance times sine of theta. Therefore, torque must equal 20 times 10 times the sine of 50. And when I calculate that, I will get 153.21 Newton meters. This would be absolutely incorrect, however. You have to remember that the angle must be the angle between force and distance, and in this case, this is not the angle between force and distance. That would be this angle up here. This angle is just the angle between the distance, that pole, and the horizontal. So this doesn't have direct bearing between the angle of the force and the distance. If I did redraw this, however, and I just extended these, you can see you form a right triangle. If this is 50 and this is 90, this angle must be 40. That's the angle between the force and the distance, so I can now use this equation. So the torque in this situation would equal 20 times 10 times the sine of 40, which would give me 128.56 Newton meters, which you can see is more accurate. It is not the same answer we got before. This would be the actual torque generated by that force. So the big takeaway here is you can always use torque equals force times distance times sine of theta, provided that you always use theta as the angle between the force and the distance.